So thanks for coming. I'm Juri Lelli. I'm working at ARM. Basically, I'm still working on a scheduling thing. I will talk one on the last slide that's introducing what we're actually working on as the main thing at ARM these days. But I wanted to come here to give you it's basically both an introduction and a status update about this shared deadline thing. Because I was basically working on this thing when I was back during my PhD. Worked for 3 years on this thing, and then now that is actually mainline, I trying to find time helping maintaining this thing, and hopefully in the future I will have more time to actually developing it further. I'm not sure if how many of you are already familiar with it? Okay, one, I know. Two, a couple of guys. Okay, so I guess, I was thinking that maybe not many of you are already heard about this thing, so I will give you a general introduction on what it is and what it is implementing, why is it different with respect to, let's say, the usual scheduling classes and policy that were in Linux since many years. And then I'll go and present what are the topics under discussion in these days. There are at least a couple of patch sets that are under discussion in Linux community list. And I'll talk about what they are implementing and what they are there for. And then I'll basically give you an outlook of real future work. So stuff that is, there is already code for some of those points there. It is not yet ready for presenting that on Linux community list. There are already papers, so the theory is there, but still requires more work to be presented on a mini list. Anyway, let's start with the basics. So what is it? As the name might suggest, well, if you look at the name, you just think, okay, that's about deadline, but it's a little more than that. It's relatively new. This thing has been added to the mainline Linux scheduler since 3.14, so I'd say like at least a couple of years ago, something like that. It has been developed for several years before that thing, at least 7 or 8 years. It was a university, so an academia thing, but then we managed to get that into Linux. It's another real-time scheduling policy. It sits above shed normal batch and shed FIFO, so it's the highest priority thing you have in the scheduler right now. And well, that is, if you look at the other scheduling policies, I mean, only root in this for now can use it. And that's, there are several reasons why this is like that right now. I will probably cover that afterwards. It's a part of the future works, why this thing can be only used by root users right now. What it does, it's basically enabling predictable task scheduling. Well, you might say that is more or less what Shed 5 or RR are already doing. I think it's more powerful than that because let's say the interface that it exposes to user space, it's more powerful in the sense that it can be used to tell the scheduler more information about what is going to be scheduling. You'll probably understand that better in a while. So it allows this explicit per task latency constraints, and it is, I think, one of the strengths of these new scheduling policies. It is able to avoid starvation. So the starvation avoiding, it's basically built in the mechanism itself. And that is something that is, for example, not true for Shed FIFO. And in general, it is useful to enrich the scheduler's knowledge about the, in general, quality of service requirements of user space. You can basically use this thing in principle to service kind of hard real-time type of workloads. But I guess, and I actually experimented with it, and it's, I think it's useful even for these soft real-time cases, at least for some of them. Oh, by the way, if you have any question, please interrupt me. It's probably easier to service them than leave them at the end. OK, I guess this is the really high-level view of what you can get by scheduling a task with shared deadlines. So in the simple example, you have 4 CPU-intensive processes running on this 4 CPU system. You see that in the left side of this plot, they were using shared normal. So basically, they were hogging the CPUs. Then when you attach shared deadline reservation to those tasks, they start being executed. Basically, they become periodic in the sense that they are scheduled on a period base. And so it's, there is more control over those tasks. And another thing to notice is that they don't interfere with each other. Well, in this case, even before they were running on different CPUs. But if you think about, I will add another task to the system, this thing will be co-scheduled with the others, and it won't interfere with the execution of the other guys. But I mean, this is really a simple example. So yeah, just to talk about this a little bit again. Basically, the current Linux scheduler, it's a framework composed by different scheduling classes that can implement one or more scheduling policies. Right now, you have the fair.c that is implementing 3 scheduling policies. You probably, I don't know, 90% of your usage is shared normal, so it's the default CFS scheduler. It's basically servicing best effort type of work as well. It's actually used maybe improperly to actually service also latency type of workloads, like, I don't know, in the mobile space or these kind of things. But probably because there wasn't a solution targeting the latency sensitive workloads back in the past. Anyway, then we have RT.c that is implementing Shed5 or ShedRR. This is the traditional priority-based scheduling that is priority-based and then round-robin scheduling with priorities. And deadline is the new addition that is implemented right now, only the shared deadline policy. So what's the policy about? It basically implements more than the classical earliest deadline first scheduling. Earliest deadline first is pretty simple. Basically, the priority is given by the deadlines of the task. So whoever has the earliest deadline gets executed first. It's pretty simple. But on top of that, and I think that's the, well, yeah, that's the cool thing. It also implements this constant bandwidth server. And basically, this guy service it actually computes the deadlines that the scheduler uses at runtime to schedule tasks. This is kind of tricky. So I try to come up with a couple of simple examples where having the CBS on top of EDF makes a difference. So let's see this simple example. In this case, you have 2 tasks running on a single CPU. Tile 1 runs for 5 time units every 9 time units, so they are both periodic. And Tile 2 actually runs for 2 time units every 6. So in this case, well, the overall utilization is around 89–90%. And the theory of real-time system, in this case of EDF scheduling, tells you that on a single CPU, you can actually reach 100% utilization, and your task will be meeting their deadlines. And this is actually the case in this simple case. So Tau 1 start before tau2, so it gets executed, but as soon as tau2 is activated, since it has an earlier deadline than tau2, it preempts tau1 and then can execute, and when he finishes executing, tau1 can go on and complete its execution. So everything is working right, so the theory was right in this case. But then comes reality. So in reality, you can do you can put bugs in your implementation, or simply things can be different from what you expected. I don't know if for example tau1 was part of rendering pipeline, maybe it got a frame that was slightly bigger, so it spent more time executing the rendering. So it might be executing for more than 5 time units. So what happens in this case? So if tau1 in the second activation goes beyond the 5 time units, since it is still it will still the earliest deadline in this case, it will basically not let tau2 execute up until too late. So basically the execution of tau1, the bad execution of tau1 will jeopardize tau2. The two tasks will interfere with each other, and this is not nice. I mean, this shouldn't happen. Another thing that can actually happen is that, for example, even if tau1 is it's actually behaving, let's say, right, it might sleep. So the EDF theory wasn't actually accounting for tasks that were actually, voluntarily sleeping for, I don't know, waiting for IO or whatever. So in this case, for example, tau1 goes to sleep right after its second activation. That is activated together with the third activation of tau2. And since it has the earliest deadline again, it will generate a deadline miss in tau2. So, I mean, this thing can happen on a real system. So that's why that's where the constant bandwidth server comes into play. What it is? It's basically a resource reservation mechanism. In this case, our resource is the CPU time, and basically the definition is that the task, once it's associated with a CBS reservation, it can run for Q time units. This is basically what we call the runtime in every interval of length p, which is the period. So you might remember the first plot that we saw, second slide or third slide, where when I associate a reservation to a task, that thing becomes periodic. So that's basically that's the runtime, and that's the period I associate it with the task. Let's say the tricky part here is that this CBS computes reservations, dynamic deadlines, and those are used by the scheduler to actually schedule a task with EDF. This is kind of tricky because basically when you specify, the interface that you have, you specify deadline for your reservation, and then maybe you expect that thing to be actually used and consumed by the scheduler at runtime. This is actually not true. What you specify is, it's basically the parameters, it's basically a description of how much time you will need in every interval of time. But then what the scheduler does is basically a different thing. But the nice thing is that this thing that the scheduler does allows you to be sure that your guarantees will be always met. Anyway, it's probably the next few slides will be easier to understand what I'm talking about. Yeah, I guess I already said that. So we have EDF giving higher priority to more urgent, so earlier deadline tasks. And then EDF and CBS, the conjunction of these two things, provide what we call temporal isolation. So the fact that a misbehaving task won't ever affect someone else in the system. How this thing is actually working. So you remember the first problem that we had with plain EDF. So we had tau1 was the bad guy in this second activation and was causing a deadline miss in tau2. So what happens when you have the CBS in place is that tau1 won't be allowed to execute for more than 5 units that was actually declared beforehand. So it will be stopped until basically when he depleted its current runtime. So tau2 will have a chance to actually run. So and will meet its deadline. Of course, tau1 will probably miss the deadline if anything, but that's the problem of tau1. So I won't jeopardize tau2 work in this case, and that's basically what we need. That was the easiest case because I just need to stop the task. The trickier case was regarding the sleeping inside a reservation. So you remember that the plain ADF had that problem that when tau1 resumed execution together with the third instance of tau2 was causing a deadline miss in tau2. What the CBS thing does is it's basically when tau1 wakes up again at the same time than before, the CBS will apply one of its rules and will recompute the deadline, the actual dynamic deadline used by the scheduler internally of tau1. So in this case, you see there are basically 2 deadlines for tau1 at the end of the execution. So it will basically postpone tau1 deadline afterwards. In this case, it will be after tau2 deadline, so that tau2 can be put to run, finish the execution, and won't miss the deadline as in the first case. Is that understandable? It's okay? Yep. Yep.
So in the previous slide, task 1 not making its deadline, that's task 1's problem, right? It's going to, if it went too long, it's going to miss its deadline.
Yeah.
You know, that's the problem in task 1.
Yes.
There's no way, there's no way you can schedule around that.
Yes. Yeah, and also here, I mean, in this case, it will probably, it might be missing deadlines, but that's probably because the design of your system was wrong as well, because probably you didn't account for sleeping, for example. But still, the thing that you did wrong for tau1 won't affect tau2, and that's a good property, I think. Okay, so that's basically what the basic mechanisms are doing. And that's why it's basically different from, for example, SHA-FIFO. Still based on deadlines, but you don't have this nice mechanism that can give you guarantees. Yeah, more on this. For example, what happens for load balancing or priority inheritance. For load balancing, we basically have more like the same implementation that we have for SHA-FIFO. So it's still based on push and pull mechanism. It's an active thing. So basically, every time I get a new task that wakes up, I want to be sure that this guy gets executed if need to be. So I will push this task away if it can execute on the current CPU, and we'll try to pull other tasks when, for example, a task is finishing execution. So the rule that is actually implemented is called global DF, and it says that on an M CPU system, the M earliest deadline ready tasks are always running. And of course, we respect task affinity and CPU sets constraints, but that's what we want to achieve. Regarding priority inheritance, what it is, this is one of the big future work items, because what we have right now, it's really the basic thing to make this thing work. We are actually implementing deadline inheritance, which means that when a task is boosted by someone that blocks on the same music, the task inherits the deadline of the donor. So traditionally you inherit the priority. For example, in Shell FIFO, here you inherit the deadline. So that's basically a priority thing. It's a suboptimal because the problem is that, since in principle, we should inherit the reservation. So if you think, I mean, if I have, I could, in principle, donate my reservation, so my runtime, a deadline, to whoever I want to get it run and finish quickly the work that has to be done. It's kind of tricky. I will detail about that afterwards. And it's probably one of the reasons why this scheduling class can only be used by root right now. Because if you allow non-root activities to use this thing, might be basically used wrongly, and you might be screwing up your system in some cases. Just a common question. I want to answer this question because I usually get this question. So how does this work with preempt-RT? Yeah, well, it should work good because basically it's an orthogonal thing. This is a scheduling policy. So it basically, it's meant to be able to schedule your task. Preempt-RT, it's a different thing. It's basically targeting reducing latencies. And so it's really orthogonal. So it's actually, they should work together with any problem. We have the thing already in the preempt-RT. And as far as I don't know, maybe.
A few bugs I found.
Yeah, apart from few bugs, they should work properly. So it's really orthogonal thing. I guess the two together will be, of course, useful in a real-time system, I guess, because you can. Okay. Yeah. Okay. So they are actually used. Yeah. As a general comment, the problem that I basically have is that I'm basically sure that someone is actually using this thing, probably also in production real system. I didn't ever have the chance to speak with these people, and basically every time it's like, yeah, we might be evaluating this thing and this, but didn't have, so it's good to know that it's actually used. Okay.
It'll be used more soon.
Okay, good. Right. Yeah. So just wanted to spend some time to see how the API work. So you have basically when there is a new syscall that you have to call to associate a guarantee, a reservation to your task, and you have to specify 3 parameters in this as part of the API of this new syscall. This is basically runtime, deadline, and period. What are those parameters? So let's say that this is a simple execution of a task. So let's say you have an activation, then you have some runtime, maybe a deadline, and then you have an next activation. So of course, the period, it's simple because it's basically telling you how much time between 2 consecutive activations. Sorry? It's shed set after. It's after. It's in the next slide. So yeah, maybe I can go backward. Actually, it's probably easier to understand with this slide because we also have the thing. So that's the new. You have 2, but one is set and the other one is get at. So you have to specify of course, the PID and then a set of the attributes and some flags. So the attributes you see at the bottom of the structure, you have shared runtime, deadline, and period. So as I was saying, the period, it's easy. It's basically the time between 2 consecutive activations. Then you might specify deadline that is before the actual period. There might be uses where you need to specify the thing to say, okay, I'm periodic like this, but then I want to finish my work before this is in time. It's more general, let's say. That it can be, but personally, I always use deadline equal to period. You can set the thing, but it's up to you. And then I guess the tricky part here is the runtime. Because, I mean, in principle, if you want to use this for servicing hard real-time type of workload, you want to compute your worst case execution time. So what is your execution time when everything that can happen happens, and then you want to bound the thing for the thing. But in general, and especially for soft real-time system type of workloads, so when you talk about quality of service, you can actually, what you can do is basically to compute a reasonable average of your execution times. I don't know, if you are to render, you're playing a video, you can do like an average of the rendering, of the time spent rendering the different frames, and then use that as a general, I'd say as a general starting point. There is more on that on future work, but that's basically a simple rule of thumb you can use to actually dimension your runtime. And then when you have these parameters, you just have to initialize the struct there and then call the syscall. And after that, your task will be associated with the reservation. Is that okay? Right. That's the API, and that's, yeah, it's a simple usage example. You set up the parameters, and then you call the syscall. That's basically what you need to do to use this thing. Okay, just want you to show, as said, I mean, I personally don't use this thing in a real product yet, but we run a lot of experiments and we have papers. I guess, the slides will be on the site, so I put references to where you can find what I'm talking about. So there is, I think it's quite a nice paper we published last year that actually talks about all this that I'm talking right now, and has more experiments and details. So feel free to, I'm not sure if it should be freely. If not, shoot me an email. Anyway, in this case, what we were running is an example using an M player playing a HD movie. For us, the quality of service measure is the interframe time. So basically the difference between the display times of the current and the previous frame. And in general, variation in this IFT is bad. So basically, you can feel that the thing is not shown properly. So in general, you want to keep this variation without any jitter. And to test that we actually implementing this temporal isolation thing, we were running the single instance of the M player for which we were looking at numbers together with other 6 instances of the same thing. So what is plot here is a community distribution function of the EFT that we got from the experiment. Right, I have arrows. So this is shed normal, what shed normal does. So you see that the quality of the service, so in this case, the inter frame time, is actually highly dependent on the system load. You see that the best thing that we can achieve is that since, okay, so it's on the right. Since the expected IFT is 41 milliseconds, we would like a straight line there. So it means that my IFT is always like that. In this case, we have some IFT that are like in the range of 20 milliseconds, and then we can also go over the 40 milliseconds. So we have a non-null probability to get, for example, 80 milliseconds, and that's really bad. So it means that my IFT is varying between, I'd say, 5 milliseconds and 100 milliseconds. So this is quite bad. No, the CDF is basically the system load it's basically 7 instances of the M player. Here you get in, it's a measure of the IFT you get running this thing. And ideally, you want a straight line on the 41 millisecond, which means that your IFTs were all 41 milliseconds. In this case, the line there is basically the probability. Let's say the probability is not a probability. It's actually the measurements of how many times you got, for example, 20 milliseconds. So it's basically it's a sum of how many times you got a measure.
I'm clear on interframe measurement. I don't want to wrap all this here, but I was trying to figure out what you're plotting it against on the left-hand side.
Yeah, it's basically a cumulative distribution function of the IFTs that you got by running this thing.
Okay.
Yeah, it's basically a sum of the different things, and then you plot that against the IFTs. Yeah. So this is shed normal, and as you see, if we choose to run this thing, use the shed deadline, and of course, I mean the period is basically the IFT because that's a periodic thing. That was easy. And the runtime, you had to actually play with it, and that's the average thing that I was talking before. So here we actually, we actually have plotted two values. One is using 7 milliseconds as your runtime, and the other 30 milliseconds. If you see the 7 millisecond thing, it's the round point with the dotted line. It's actually behaving not good as expected, because basically what happens is that your runtime is too small compared to what you're actually using. Instead, with 30 milliseconds, you actually always have the time to render your frame. So that's basically the straight line you see on the 40 or around the 41 millisecond point. Yeah, I mean, you might say that, okay, I can probably achieve the same thing just using shed FIFO. So I set higher priority to the rendering task, and I'll probably get the 41 millisecond thing. In this case, it gives you the ability to, well, first you can use this thing to service multiple tasks, and then you can dimension them separately, and they will basically have this kind of guarantees. And the other thing, if you basically plan to use this thing, maybe in I don't know, a battery constraint system, you are basically using only a fraction of the available runtime to actually run this thing. So you might be saying, okay, if I have this spare time, I don't know, I can clock down the frequency and maybe save some power. Something that you cannot really do with shed FIFO because you don't know how much time you will be using. So it's more powerful in this way. Okay, any other question? This topic. Right. So that's basically the it's already there and what it can be used today. I will now spend some time discussing what is under discussion right now and what will come next. All right. So this bandwidth reclaiming thing. So what's the problem? Let's say what's the one of the problem of the current implementation is that basically the bandwidth that you associate with a task, it's fixed. The only way you can actually change it is calling, again, the syscall and maybe changing the parameters. But that's probably kind of unwieldy, or it's, I mean, your requirements might change at a rate that is actually I mean, things can happen too fast with you to cope with. So what happens if tasks occasionally need more bandwidth? I mean, you still dimension your runtime based on an average. So it might happen in reality that you are, I don't know, for central activation, you need more than what you got. Yeah, for example, in the rendering, still a rendering example, you can have a heavy frame once in a while, and you want to service the thing, but you still are constrained to what you ask the system beforehand. So reclaiming might help with this. Basically, it's a mechanism that allows tasks to consume more bandwidth than originally allocated. Of course, this has to be bounded up to a maximum fraction of the CPU time, because you don't want to really starve other less priority activities. And of course, it has still to guarantee others' guarantees. So you don't want to go back and jeopardize work done by someone else. Yeah, I won't give many implementation details about this because it's basically digging in theory and stuff. So it's basically implemented as this thing is called greedy reclaiming of unused bandwidth. It's basically a modification of the CBS that we saw, and basically slightly modifying the rule for replenishing the runtime and also the postponing of the deadline. You can achieve this nice reclaiming thing. It will be nice to actually use it. I'm not driving this. That's Luca Beni. It's a professor at University of Trento. He is actually the original author of the CBS, the theory behind the CBS. He's actually proposing patches on Linux kernel release this day. Actually, he released the second version of this thing like yesterday, so it's really something that is happening right now. But yeah. He's driving this. Yeah, I put the reference there. It's already outdated because I prepared the slide three days ago, and yesterday Luca came up with a new version. So, but I mean, that's good, I guess. That shows progress. Results for the thing. So in this case, the workload is really simple. It's a full synthetic thing. I guess well, there is probably a result. There are probably results showing the case we saw with the employee RHD. So basically, you can run the same thing again. In this case, just to show how the mechanism can be benefiting tasks, we have two tasks. The first one has 6 milliseconds of runtime and 20 milliseconds of period. And it is actually a cost and execution time type of task. So it will always run for 5 milliseconds. So it will always run less than the runtime it was granted for. So it should be always well. Task 2, instead, it is granted for 45 milliseconds every 260 milliseconds. So that's what he is granted for. But however, it will experience occasional variances in his actual runtime. So it will, each activation can run between 35 and 52 milliseconds. So it will could actually go over the runtime it has been granted for. And this is what happens. It is evident in the plot. It's basically the same kind of plot that we had before. Instead of the IFT, you have the response time. So it's basically the time that an activation finished. Is the same thing. You see that. Okay, so this is what happens when you use plain CBS. So what you have right now in mainline to service T2. There are cases in which the response time is bigger than the reservation period. So in this case, you will be basically missing deadlines. So yeah, of course, because you are stopping the task to run, and then there is workload that is accumulating, and you will miss deadlines. Instead, if you use grub, you will be basically taking some of the spare bandwidth that task 1 is not consuming and donate that to T2. So even if T2 can execute for more than is allocated runtime, it will be still be able to always finish before the reservation period. And I mean, the nice thing is that this is something that you don't have really to control. I mean, you just specify, it's basically a flag that says, OK, please use the reclaiming mechanism to schedule this task. And then the scheduler will do it automatically without any user intervention after that. So it's something that can actually happen at any rate. OK, so that was the first thing that is under discussion. It's I think it's actually pretty powerful mechanisms to service a wider range of use cases. And it is actually nice to have that thing because we can use basically the same mechanism to service another type of use case. There is, in the last, I guess, few years, there was under discussion on a mailing list this thing to integrate more closely the frequency selection within the scheduler. So I was part of this thing. There's also Steve Muckle here that is now driving this thing. And Rafael Wisoki has actually proposed a different solution that is now, I think is going to be merged quite soon. And also Mike Tarquette was originally developing this thing. What it is, basically, yes, it's basically a scheduler-driven CPU clock frequency selection. The idea is that basically each scheduling class has to provide hints to what is the required OPP. So what's the required frequency your CPU has to run at to meet the user expectations. Yeah, why the bandwidth thing can play a role here? Because basically, the problem that you have if you use shed deadline as is right now, as you know, what you ask for, so the runtime over period thing, it's actually quite a pessimistic. Usually, it's a pessimistic view of what you really need when you're running in the system. So you can use that thing. Basically, if you divide the runtime by period, you get the utilization of the task. And then you can use that utilization to select an OPP, so a clock frequency that will give you that amount of CPU time. But since the runtime over period is usually a pessimistic thing, you will be most probably consuming more, let's say, more energy than what needed at runtime to service the task needs. So another point of this static view of the system is that task serviced by shed deadline has not to be strictly periodic. They can be what is called in RT theory sporadic. So they will be, the guarantees will be there, but only when the task is activated it's actually coming to play. So the task can be admitted to the system, but then it will be used its own bandwidth, maybe, I don't know, some second afterwards, because it will be, I don't know, woke up by certain events. And if you don't know if the bandwidth allocated to the task is actually used by the system right now, you might be, I don't know, keeping for example, the frequency higher just because the task was there, but it's not running. So you don't really know if you don't track what is actually being used right now in the system. And that's basically what the bandwidth reclaiming thing does. There is basically the first patch introduces this runtime tracking of the bandwidth used right now by the different tasks. And then you can, in principle, use that thing to scale down your frequency. More than that, there's probably a step further. You can, in principle, think as you donate what a task leave in the system because it's not using that to other tasks, you might be thinking that you can actually, instead of donating to other tasks, you can actually use that spare thing to further reduce your clock frequency. So maybe achieving further energy savings. That's another possibility. So there are different possibilities, but for sure we need the runtime tracking of the different tasks. That's one thing, and that's a good thing that it's already part of the previous of the patch set that I was talking about previously. Okay. Right, so that is basically what is already on the pipeline. I think I have like 5 minutes or something like that. Okay, so I will try to be fast here. Future work. One big thing that is actually missing is group scheduling. So right now there is no group scheduling support for shared deadline. What you can do is associate one-to-one a guarantee, a reservation to a task, but will be pretty useful to be able to associate a runtime guarantee to a group of tasks. Yeah, for example, I don't know, virtual machine threads or a full rendering pipeline. You can basically, in principle, think, okay, I will put all the tasks in a single thing, and I will get a guarantee back to back. It is, well, it's probably should be easy to implement from a technical point of view. There is actually already code somewhere. It's also already presented by another guy in one real-time Linux workshop. But the problem is that still there is, from a theoretical point of view, there is still some thinking to do how to properly isolate, let's say, the global scheduler. So it's basically the level 1 scheduler with respect to the local scheduler. So if you think that each group will be serviced by another scheduler inside the group, how to basically give guarantees to this guy here without basically having any information switch between the two. That's a theoretic thing. That is. And yeah, once the thing is there, I guess the plan would be to replace the FIFO-RR throttling mechanism with this thing, because it's basically doing the same thing, but it's more general. And so it will be probably easier to use, even if already there are like problems like, for example, the affinity things that we were talking about. Anyway, and it might be a practical solution for, yeah, this forking question is a problem that currently shared deadline tasks cannot fork because we don't actually know how to distribute the reservation guarantees to the children. And so thinking of, okay, maybe I can associate a group with a task, and then when this guy generates children, they can basically share the same kind of bandwidth guarantees on the same group. But that's, I don't know, it's really future thinking. Another thing that might be interesting to have is a dynamic feedback mechanism. This is basically to be able to exchange information between user space and kernel space. So let's say that I associate a reservation to a task, and then this task starts to behave wrong because maybe I was giving him not enough runtime. It would be nice to have like a mechanism to say, okay, user space or any kind of middleware, please enlarge my reservation because it's not enough. So this thing will be probably working together with the feedback, the bandwidth reclaiming thing. It's probably a lower rate type of adaptations. And yeah, as I said, we had to enhance the priority inheritance. This solution should be the bandwidth inheritance. So I'm actually hereditating. It's basically similar to the proxy scheduling. So I can schedule another task inside the reservation of the donor. And that thing will be, yeah. But yeah, they should work. The problem with this thing is that it's not super easy to implement this thing on a multiprocessor system for both theoretical and practical issues. But I mean, it's something that we really need to implement. And well, a general thing is the energy awareness. So I was already talking about switching clock frequencies. Probably, I don't know if you're already familiar with this energy-aware scheduling thing that is going on the Linux kernel mailing list. But basically, I'm participating on this effort to make the Linux scheduler more aware of both energy and performance. Right now, it's basically focused on throughput, so it doesn't take into account energy, I'd say, much. And of course, but right now we are basically focused on CFS or shared normal. We should, of course, extend this solution also to the other scheduling classes, and shared deadline would, of course, be one of those. Basically, the idea is that I have an energy model of my system, and then I can consult that when I have to do scheduling decision and load balancing decision. And that energy model has to be will be consumed by shared deadline as well in the future. Yeah, of course, if you're interested in this energy-aware thing, please come to me even afterwards, and I'll give you more details. I don't have much time now to detail about that, but yeah. Or shoot me an email. All right, conclusion, since I guess we're running out of time. I'd say the general impression I actually have is the kernel space has already some feature that can be used as is to service quite some workloads, minus some bugs that we had to fix. But and there is already work in the pipeline that is happening or it's planned to happen. So I guess for the kernel side, we have a pretty fair story about this thing. What I personally, I was just saying previously, the user space usage of this thing, it's personally still lacking something there. So please come to me and tell if you are using this thing, how you're using it, or if you are interested in how to use it, I can, of course, give you much more information. I mean, I experimented myself with different things. For example, it's a KVM, can be, service virtual machines and provide quality of service guarantees to those might be a thing. Or in the automotive space, maybe it will be interesting because it's basically a real-time system. And of course, personally, I'll probably dig into the Android space, so the mobile multimedia field in the future. So it will be another place where to play with this thing. Okay, that's basically what I have. And if you have a question, or if we have time for a question. Yeah. Right.
Suppose I have to write an application with the deadline scheduler requirement, and I want to run this application on a
Yeah, that's working.
Suppose I want to write an application which needs a deadline kind of scheduler, and I want to have this application applicable for multiple platforms, which some of them will be faster than other. So how to write this application so that it can give right kind of runtime on each of those platforms?
Yeah, I think, the question was how can I write the same application, this thing work on different kind of platform that might be, I don't know, different capacity, let's say, features. I guess this is highly connected with these bits here. So the energy-aware scheduling thing is actually both giving the scheduler a power information, but also capacity information. So in the energy model, we have like different capacity levels for example, the different OPPs of your platform. So in principle, if you, right now it's, the API is only time-based, but in the future can be actually, I think it makes a lot of sense to actually be capacity-based. So, which is basically the same thing. So it's a fraction of the scale that you have. So if you have 1024 max capacity and you want 10% of that, the 10% should be the same. I mean, you can specify 10% of the maximum capacity, and that thing, it will work across different platforms. Just because the different OPPs of your new platform will be giving you different capacity levels. But since you specified your reservations on a relative scale, they will be met as well. It's probably, right now, it's, I understand that there is some tuning to do when you move to a new application. I guess when we reach this level of thing will be easier to achieve.
Yeah, so 2 questions. Yeah, okay. Are there statistics to know that you've exceeded your runtime?
Sorry, can you?
Are there statistics being gathered as to if and when, how often you've exceeded your runtime?
Okay, there are not yet. This is part of the other bits that I was, of the dynamic feedback mechanism. I mean, what I was thinking about is that how can I get information from the kernel that I'm actually, I don't know, missing deadlines or I don't have enough runtime to actually run. So this is something that it was part of the original posting. Then we decided to remove that thing for merging the bulk of the mechanism, but that will be, it should be fairly easy to extend that farther now. So yeah, actually, if we have a use case for that, it will be easier to basically push again in mainline the solution, because the solution can be easily achieved.
The other question is, have you written the static trace points for the runtime and period events?
That's a good question. I think, I don't know if Stephen.
Yeah, it's the trace points have been posted. Right now, Peter Zylstra is kind of reluctant to accept them. So right now we're going through negotiations with mainline on what's acceptable, because once you get trace points out there, they kind of become an ABI. So you have to make sure they're correct. So right now, there's back and forth going on to make sure we have something that could be stable in the with future enhancements.
Yeah.
I was just curious how much you've seen and people who've tried to use this, and this is kind of a follow-on to his question. I mean, even within the same platform, CPU frequencies got to play a huge role in determining the policy for CPU frequency is very important, right? And how you specify your runtime. So, I mean, how would you expect that to work today? I mean, with someone who's, say, using the on-demand governor interactive or something, I mean, unless you're using some straightforward thing where you're plugged into a wall and you set perf governor, you kind of have to, I guess, assume fmin, right, and assume worst case time, but then you're leaving a lot of time on the table, I would think, in the acceptance of deadline work.
Yeah, so, well, I guess right now, without considering the shed frec or shed util solutions, I guess the only thing you can do is just to use performance. It's the usual RT thing, and then you will be meeting because you're not basically using the frequency switching thing. I guess that solution will work once we have the scheduler in full control of the frequency selection. In that case, you will be basically aware of the fmin that you need to service shared deadline things. So that will start to work. It's not yet there, but we need that kind of integration, of course, to make this work. Yeah.
That's often the case if we have applications which target into the hard real-time space. Because we do not have that.
Be recorded, so you're not being
That's a side of using deadline today the case if you target applications into the hard real-time space, because we don't have the mechanisms in the kernel yet to actually give you a sensible information about what your system is going to look like if it runs at half the speed. Yeah, so that's definitely something we need anyway for further improvements, but independent of SCAD deadline.
Yeah, that's why it's one reason more why we really need this integration within the scheduler of the frequency selection. Because, okay.
So you mentioned this only works for root processes. How would you suggest? Well, normally want to run audio mixers just with some very specific privilege. How would we, do that, or is there going to be some support in the future for being able to whitelist processes integrated with, Mac, SE Linux enforcement and stuff like that?
I guess the once we solve the issues that we have right now, for example, for priority inheritance, I guess that's a blocker to actually extend this thing to be used by non-root type of activities. So it's not, in principle, it's not possible.
I don't think it's necessarily root. You have to have the permissions like you have to do for RT scheduling. Yeah. So you can, there are access controls for it already, or what is it?
Right now it's...
Capabilities.
Yeah.
So it's
Yeah, we
it's
can
a
easily extend that
capability
thing.
aside of which you can assign to any given user.
Right. Thank you for.